And good evening. Today I'm going to continue working on the neural network. I have been kind of working on it for a while now. I'm on my second version. The first version became unnecessarily complex, so I decided to redo it after I accidentally also broke the first version. Anyway, I'm gonna start up the programs I'll be using. Let's see. We have a terminal here. We're gonna go to Ubuntu. Let's see what files I got here. Let's see, so it's encoding. And encoding we have new NN probably. Yes. Okay. Just for the interest of people, I might also bring up some of the math behind this on the side. Let's see if I can find it. That's probably it. Yeah. See if we can line these two bits. Oh, no. I will instead like so, and Visual Studio like that. Okay, perfect. So where was I? We start off by importing the libraries we're using, NumPy and Pandas, also ABS for abstract classes and methods. We import a given dataset, do a quick analysis of the data we got. We have these attributes 1, 2, 3, 4, 5, 6, 7, 8 attributes and one label. We only have 1030 entries, which isn't a lot. Let's add a markdown here. So 1003 might not be enough for this, but we'll give it a try. Okay, here we have a class called math. This is where I put all the like basic mathematic formulas. So ReLU, which is an activation function, the derivative of ReLU, which is used for backpropagation, and then we continue to the neuron. We also have our types of layers here. We have some abstract functions here. We have a base layer type, with dense layers, input layers, and the model. Okay, let's see. We're doing the start. We can. I actually tried running this last time and got some strange output. Let me show you. So we have this output. This is just pure madness. So the idea is to move the math from the layers to the neurons. So let's look at the forward propagation. So on the model we have a method called predict. Predict first checks the size of the input so that it fits the model. Then it sends the input to the first layer, the head layer, which is also the input layer. So we're going to scroll up to the input layer. What do we have here? We have just a simple forward. Since the input layer doesn't have it doesn't do any math or doesn't have any neurons, so we can just pass it through basically, and it gets passed on to the next layer, and the next layer is a dense layer. Dense layer, or you can call it hidden layer if you want to, because it is also a hidden layer. And the hidden layer, let's see. Oh, dense layer, sorry. We have the forward function, and it creates an output array. Okay. And for each neuron, we do the math here. So let's move this math from the layer, move to the neuron instead. So we're gonna create a variable called neuron output. Neuron, let's calculate output, sure. That describes it enough. See, oh, welcome to the stream, by the way. Okay, we have we can type in neuron output. Wait, what do I have here? So if next layer is not none, pass it forward. Yeah, so what we're doing here is that we're checking if there is a next layer, then we pass this output to that layer so you can continue the calculations. And if there is no next layer, then we know that this is the output layer, so we can just return. Okay, so let's go to the neuron class, and we need to define a method here. So we apply the weights and bias to input data, and it can probably do this for us. Yes, okay. So we have a calculation function here, we have the input data, and we take the dot product of the weights and input data and add the bias, and just return that. It's super simple, really. If you know linear algebra, then I'm not sure if you guys know linear algebra, let me know otherwise, and I will tell you about the basics. And I wrote calculate output instead of calculate. Let's go calculate as Copilot suggested. It is cleaner. Okay, if you scroll down to the output, we should still have the same problem. Yes, we do. Okay, I'm gonna scroll back up. I want to know the output of each layer. So let's print out the output here. Maybe first we will print out the identity of this layer, so you can backtrack this. Okay, so just this dot name, maybe? Oh, self.name. Sorry, wrong language. And we're gonna type one more print. Let's see. You can format that like output. Okay. Do have the first dense layer, and this is not right. Wait, is it? What's going on here? So we pass. You know, let's go to the input layer. Input layer. Print out self.name. We can also print out inputs. Let's run this. And okay, so the input sends this array. This is correct. So this then should be sent to each neuron. Let's scroll up then. We have our dense layer, and here we loop through the neurons. We'll calculate neuron output by sending the input to that neuron. We append it. This is strange. Let's also check the outputs of the neurons. This is the output of the neuron is not the full result of the pre-activation function, but it's part of the result. So let's call it part Y, I guess. And we can print this out. Like that. Okay. So the new results are apparently vectors. Why? Where is the weights, input data, bias. Input data is 4-dimensional. No, 1-dimensional. Down to. I'm gonna check the input data it gets. Okay, so this is the first neuron. It has that input. Okay, this is strange. I can print out the weights. Sure, we can do it like that. The bias of it. Maybe I'll just print out an empty line. Okay. Yeah, here it is. This is a 2-dimensional array, which is wrong in this case, since the math have been split up. So wait, hold on. Yeah. How do you say it? I'm gonna bring up Paint to try to explain it. So the normal math for a layer is we have our activation function. No, sorry, the pre-activation function. Take the weights transposed dot product the input plus our bias. Then we take this result, plug it into the activation function. Let's call that whatever this sign is called. Like that. So the weight matrix here is a big one. So for instance, we will have the weights for the first neuron, second neuron, third neuron, and oh crap, fourth neuron. And we'll take dot products. Never mind, we want to say dot product here. So what we can do here is that we can split up this math. So we can, for instance, do y1 equals just w1 transposed dot product x times b, b1, the first bias. So b, by the way, is also a matrix, or oh, just a vector, I guess. Okay, so if we go back now to this, we know that something goes wrong when we add the weights, but we also know that bias is correctly added. So let's go to yeah, where should we go? Add neuron. Here we have it. So the weight should be number of inputs. Yeah. Just do it like that. This should solve the problem. And it did. But we see here though that the prediction is of an array. We could flatten that if you want to. I mean, why not flatten? Just add it there. And wait, you can't flatten. Okay, I don't know. Maybe not. Let's leave that as it is. I'm gonna remove all the printing we added. There's one thing missing now though. The activation function. I think we're gonna add the activation function, the result of the pre-activation function to the activation function inside the layer. Because activation function, I don't feel like it's not really wait, should we? Does it make sense to actually have the calculations in the layer after all? So the neurons have the weights. No, we're gonna do the pre-activation calculation in the neuron and then the activation function calculation in the layer. So it's gonna be y part y. Then part A is self.activation function, and we pass part y there, and we append part A. And we're gonna move a part of this comment to the neuron. Don't need that anymore. Don't need that either. Okay, let's see. We're gonna add a comment here. So the pre-activation function is handled inside each neuron. pre-activation function, and should A be capital letter here? I don't know. And the activation function is applied in the layer. Okay. Beautiful. I feel like I need 3 hashtags there to make it smaller. Okay. If I run this again, still works. Seems like the input layer still has some printing to it. I'm gonna remove those two. Okay. So now we actually have working predictions, but we gotta make sure that we can train it now. So as you can see, the outputs down here change every time I rerun this. That's because the weights and the biases are randomized upon initialization, while the input remains the same, 1, 2, 3, 4 in an array. This is good. This is what we want. Okay. So now it's time for the back propagation. Oh, this one. So to the right on the screen, you can see most of the math behind backpropagation. This part. It's a very clever algorithm that basically checks how the cost function, which is a way of calculating the performance of the model, is affected by each set of weights and biases. So we calculate derivatives and pass those on and go deeper and deeper. And then we do this multiple times until we have found some desirable outcome of it. So we gotta decide if we will use gradient descent or stochastic gradient descent. There is a difference to them. Let me Google. Okay, let's see here. I think you can read that, probably. Okay. If someone in the chat has also a clear explanation of this, just send a message. This is the number of trains. Okay. So I'm thinking maybe we should go with stochastic gradient descent. Let's see, initialization. Randomly initialize the parameters of the model. The parameters are the weights and biases of each neuron. Okay, set parameters determine the number of iterations and the learning rate. Alpha for updating the parameters. Stochastic gradient descent loop. Repeat the following steps until the model converges or reaches the maximum number of iterations. Okay, shuffle the training data set to introduce randomness. Okay, maybe we should start there. Just because we don't know that much about this data set. It might be somewhat sorted and might not be. But wait, let's check it out. We have the file here. Maybe it is pretty much random anyway. Yeah, I don't see a clear pattern here anyway. Yeah, it's pretty much randomized. So let's not shuffle it. Compute the gradient of the cost function. Okay, so we're gonna create the cost function first. The cost function we'll be using is mean square error. This bad boy. So basically it how do you describe it? You get the you have these 2 points, a predicted value and actual value, and you subtract one from the other and end up with the distance between, and then you square that so you get the area. You sum up all the areas for each prediction and true value and then divide them by that same amount of prediction, so you get like the mean squared error. That's a good explanation of it. Because we're gonna go to math and mean squared error. Yeah, that's the loss function. So Copilot is gonna suggest the whole function here, as you'll see. So it is static, MSE, yes, mean squared error, and y hat. Okay, so let's rename this. So y predicted and y true instead of y hat. So y pred, y true. So we subtract, we square, and we take the mean value. However, note that this is done using NumPy, so this supports this for matrices. Which do we want that? I think that might be a good idea. Though we have to make wait, does this? I don't know if NumPy supports integers as inputs. Oh, here. Let's do a quick experiment here. Math.msc. I'm gonna add like the predicted value is 1, but the true value is 2. I don't know. Apparently it works. And if we create 2 arrays. Okay, so these are lists, these are not arrays. Okay, yeah, that works. Okay, we're gonna delete that. Another way, the mean square error, we can do a test. So whenever you build a model, it's good practice to first of all make sure that the data is shuffled, but also split it up into training and testing. So let's say that you have your data set here. Then we might want to take this section for training and this section for testing, because you don't want to test the model on data that it has been trained with. It's like the same reason why exam questions aren't the same questions as in the textbook. Okay, so there's also one more set you can split up to, and that is the validation set that you can use to fine-tune the parameters. Maybe let's make it simple and not split it up for now. We can add like future things to fix here. Things, let's just add list, call it to do. Split up set into training, validation, and testing. Also shuffle the data set. Okay. We're gonna scroll down. Wait. Where are we going? Right. So just for fun, we're gonna test the model before the training. Let's see. And maybe we could draw. Oh, let's just do this manually. Or should we? No, let's create a test function. The test function will right now just return a value. That is return math dot. Oh, we might actually want to assign the test function. So these first of all has to be moved, because as they are now, they are basically static. They're not instance specific. So you can type self dot perfect. We're gonna move this to the constructor. Make some space. Perfect. I think we I'm gonna set cost function. Model dot cost function is equal to math MSC mean square error. Cost function. This is a pretty good name of it. So let's stick with that. Self dot and equals none, since it's not set when we initialize the model. Okay. We run our thing. It should work just fine. Sorry. Self dot cost function. We're gonna pass it to argument. All right. Type self there. We're gonna pass it first of all some predictions. Let's see. Let's call it just X and Y. Return the result of the cast function. X is the attributes and Y is the labels. Note that this function, this method, supports both arrays and single values. Sure. Just pass one X and Y. Let's say that we're missing one of them. If oh, that's a clever fix. Wow. Do you wanna do this? It suggests that we add a check. So if it is a list, we're gonna convert it basically to an array. I would say yes. I think that might be good. Maybe it's a redundant check, but better more checks than too few. We're not gonna do it this way. We're gonna do it this way. Yeah. Okay. And now we're gonna call model.test. We're gonna pass it the data set X and data set Y. Isn't that the names of them? We have, oh, we now split it up. Okay, so we have the data set here. We have to do some stuff to it. We need to split it up. So we need to select the attributes and the labels. So data set. Let's add a small comment here. Split up the data set into attributes and labels. So dataset underscore X is equal to dataset illoc. So all columns, all rows, and all columns except the last one, and we grab the values. Now it's gonna do same thing with dataset Y, so we can select just the labels. And if you run this and print it out, dataset X, you see here that we have, let's see, first row. We're gonna type out the shape here. Print out the shape, sorry. Oh, that's, and there you go. Okay, so we have 1030 rows, 8 columns, 1, 2, 3, 4, 5, 6, 7, 8, and then the 9th one is the label. So you're gonna check that. Yes, that is correct. Okay, so we can scroll down now, probably run everything. Nope, we could not do that. Dataset. Oops. We can't just. What did it here was kind of stupid. So let's say we need to convert X to the predicted ones. So Y pred Y true. Maybe we don't need to do this check. Maybe it's redundant. Let's remove it for now. And now we need to do Y pred is an empty array. X create inputs. And do you want to add support for predict to handle arrays of inputs. I should just be able to take one at a time. I think it's nice if we can take arrays. So let's call this inputs instead. Inputs. Inputs. Okay. Pair results. Rest is no. You know what? Predictions. It's an empty array, and then for each input in inputs, we're gonna do this. Predictions. Let's call it just pred equals, and then predictions append pred. They're gonna return numpy array, or should just return a list maybe. I think that's fine. So the test function is gonna be commented out for now. Because we're gonna make sure this is still working. Model.predict, and this will cause an error. It did not. Oh. Okay. Give it that. Inputs fits grab the first inputs to double check the size. Int has no length. Oh. Okay. So we need to fix this check. This is very wrong right now. Let's see. Can we see if we can do something with the shape attribute of this? TMP equals I'm gonna add one more block here. TMP.shape. Oh, chapeau. That's right, because it's a list. So we convert this into numpy array. Like that. We're gonna pass that into numpy array. Now we can get the shape. Oh, welcome to the stream. And thank you for the follow. I am great. How are you? I'm just enjoying my evening here, playing around with neural networks. I hope you're having a nice evening too, and that you are as relaxed as I am. Well, no. Interesting username, by the way. Do you know anything about neural networks? Or are you new to this? Ah, I'm from Sweden. And you? Oh, Shelina. That's a nice name. Ah, okay. I think maybe that makes sense with the name. California. Feels like a lot of people on Twitch are from California. I don't know, maybe it's just me. Maybe you guys enjoy neural networks. Maybe that's why I got this impression. Is it warm there now? I bet you have like... I don't know how warm you probably have, I guess 26 degrees Celsius. Damn, Celsius, you guys don't use Celsius. Sorry, I don't know Fahrenheit. Let's check the weather. I'm curious. Oh my god, it's warm. Oh my god, I feel sorry for you. I would melt on the streets. Can we... Oh, you should learn Python. Python is very fun. It's very user friendly and it can be used for basically anything. And it's used for, well, just normal programs, algorithms, machine learning, games. I'm pretty sure there's even frameworks so you can use it for websites. I know you can create REST APIs with it, but there's probably more than that you can do. What languages do you know now? Oh, an editor and a professional graphics designer. Cool. Like editor, do you mean image editor or like video editor? Or maybe some other kind of editor. Sound editor? I don't know. Sure. You can't send links in the chat, but maybe you can let me know what I should Google. I do use both. Send your Instagram name. Unless your account is private. Or, you know what, we can just be lazy. You can just send it via Discord. It's just, my username there is the same as on Twitch. Oh, okay, I sent you this Instagram. Perfect. I don't think this is the right account. I'm gonna check on my phone. Let's see. Your account is private. Yeah, I'll send you a request on Discord instead. I thought, where's my Discord? Ah, there we go. just sent you a request so you can reply to that one. Let's see. Was adding some checks to the model here. In the prediction, the inputs. If inputs.shape the second element, so index 1. It's something like that. Yes, maybe this is correct. Tuple index out of range. Ah, okay. I'm still waiting for you to reply my request. Oh no, I sent it via Discord, sorry. Maybe I was a bit unclear. Welcome to the stream, by the way. The second person who joined. I hope you two are having a wonderful day or evening. So we want to double check the shape of the input arrays, and what we want to make sure is that the second over here, so we have 4 rows. How should we do that? We can't just grab it. Tuple index. Can we type length? Yeah, that should work. Okay, we're gonna go to the model. Under prediction, we first convert the inputs into NumPy array. Then we need to check wait. We need to check that the length of this is greater. It's actually equal to 2. So if it's not equal to 2, or if the number at index 1 is not same as the head layer's input size, head layer is also the input layer, then we know the input size is not correct. This could work. Yeah. Input size is not correct, as it requires this to be 2-dimensional. Perfect. We should add support so we can just send a 1-dimensional one, but first we're gonna see something on my Discord here. Hold on. Okay. I saw your message, by the way, and yes, I would like to see what you're working with. Okay. By the way, if you have like a coding portfolio or like web design portfolio, I would love to look at that too on the stream, if that's fine. so let's go to this. So you convert it into a NumPy array. What happens if you pass a NumPy array into a NumPy array? Just out of curiosity. Let's add a code block down here. Not sure what this is gonna do. Ah, okay, so like nothing. Oh, that's great. That's good to know. So it's safe to pass the inputs argument into NumPy array. It cannot break it. Let's see. If the length of the input shape is 1, oh, then we're gonna nest inside another array. Yeah, that makes sense. Okay, so basically I'm gonna get to enjoy my paint skills here. They are legendary. Just letting you know beforehand. So we have, for instance, input 1, 2, 3, 4 as an array. But the predict method is created to handle 2-dimensional ones. So basically it can handle not this alone, but it can handle this. The difference is, as you see, it is nested. So what we can do, if you just want to send one set of attributes, we can just nest it, which is what we do here. So convert single input to the arrays, meaning this is no longer needed. Actually it is still needed, because if the person was for some reason sent a 3-dimensional array, they need to know that it doesn't work. Let's see. That's some impressive work. Well known. Okay, so basically you make graphics for all kinds of purposes, but make a lot of graphics for Twitch and overlays. That's cool. I see that some people write some code for the overlays. I'm not sure what that is about. Is it HTML and CSS they write, or what are they doing? Is this something you know anything about? I even seen some people stream it. By the way, we see here that we get the 2-dimensional array as a return from the prediction. We don't want that. We want it to be 1-dimensional, so we convert the list we get into NumPy array, and we flatten that. Poof. Beautiful. Okay, that means we should be able to run the test function. Dataset X. Oh, right, we have to uncomment the method. We have the inputs, we're gonna pass them. Oh my god, sorry, I'm being thrown around here. Ypred is solved.prediction inputs. We copy the Ypred. into the cost function alongside the true values. So y true, and yeah, I am obviously a new streamer. I've only been streaming for 2 weeks, I think, but just the goal with this is just to enjoy it, enjoy some nice community, and just force myself to talk a bit more about the code I write to learn better. It's basically forcing myself to do rubber ducking. So if you don't know what rubber ducking is, you probably do, but rubber ducking debugging. So basically you explain your code from start to the end, and by doing so you learn to understand it better and often manage to solve the problems quicker. Input size is not correct. Interesting. So why is input size not correct? We're gonna print out the shape here again of dataset X. Yeah, that won't do, because we have 8 attributes and the input shape is 4. So we need to reform this, the model we have created. So let's take 8 inputs and pass that into a network of 8 neurons. Pass the result from that to a dense layer with 4 neurons, and one with 1 neuron, and finally one with a single neuron. Okay, let's see. Yeah, and we get the result of the cost function. And as you can see, since the model have not yet been trained, it performs horrible. So this is a result from basically the cost function. Welcome to the stream, by the way. I hope you're having a great evening or morning. I don't know. A great day. Okay, so we have managed to get the forward propagation to work. That is the predictions. Now we're going to start looking at the backward propagation, which is the training of the model. But there's one more thing I want to do. I want to try to just call model.predict with dataset X. Yeah, we should get here 1030 predictions. Yeah, we do. And if we select the, let's say, the 100th element, we get just 1 and we get a number here. Perfect. Okay. So, for you in chat who have not done backward propagation, it is kind of a pain in the ass, and you'll understand why soon. Is any one of you familiar with the math to write here? It consists a bit of multivariable and oh, thank you for the follow. So the math on the side contains a bit of multivariable calculus and linear algebra. It's I could go on the whole evening about the math there to the side, but I'm gonna try to stick to the code so I don't bore you too much. Oh, but Hazel, do you also plan on learning Python, as well known we're talking about? Or maybe you guys just work together with the graphic designs. Okay. Okay. Where was I? It's gonna require some drawing. I think I want some better drawing tool, so I can write you the math a bit better. Maybe OneNote could work for this. Oh, electrical engineer. Yeah, that's a bit different. How long have you been doing that? Is it like a lifelong career, or are you also planning on changing? It feels like a lot of people go to Twitch for inspiration, even for careers. Can't use that program. I'm looking for a good alternative to Paint. Let's see. Best online Paint alternative. Maybe. Sure, you can give tips on how to grow the channel. But if it's a lot, then maybe send it via Discord. Okay, Krita. We're not gonna use GIMP. Paint.net. That sounds horrible. I used a program the other day that was great for drawing. Well, not a program, a website. Was it this maybe? This was not it, but maybe this works too. So we can draw, drag around, we have layers. Can we select stuff? Let's say I draw something here. That's not... Oh, it's like, do I have an eraser? I have one eraser here. I also need some type of selection tool. I don't see one. No, maybe? Crop and resize. No, we don't want crop and resize. We can select. Oh, okay. Let's add a background, and I think that looks nice. Gonna make this a bit thicker. Oh, actually, I just completed my degree, and now. Oh, congratulations! I hope you will enjoy the career as an engineer. So, what brought you to this stream then? I'm curious. Like, are you into programming too as a hobby? Or did the well-known just convince you? Ah, this looks good. This looks very good. We're gonna let's see. I'm gonna draw you some stuff here and explain what I'll be doing now. Oh, thank you for the message, by the way. just gonna... Oh, damn. Just gonna read what you wrote to me. Okay. Let's see. So, what I will be drawing is basically the math to the right here. So, first, we have, let's see, we have our cost function, which is affected by two things: the true values of the prediction, and I have to draw a bit smaller, I think. No, maybe this is fine. The true value of the prediction and the result of the activation function before the output layer. Actually, no, this is on the output layer. Let's say this is a 3, so this is like the third layer, and this is affected by the pre-activation function of the same layer. And the pre-activation function is affected by the weights of that layer alongside the bias of that layer. And let's see, one more thing actually. It's also affected by the output from the previous layer. And this goes on, so the output of that layer is affected by the pre-activation function of that layer. Oh. And the weights of that layer, and the bias of that layer, and so on. As you can see on the right here, under the chat, hold on, I will copy it over here too. So here we have the last layer and the input layer, and the last layer is affected. That pre-activation function's result is affected by its weights, its biases, and the inputs that we send into the model. So oh, this is confusing. Oh, so I'm gonna read your chat messages now. Got a bit carried away. Oh, I'm not thinking to learn graphics design from She and Lena. Oh, cool. I'm not earning anything from this. That's not the goal. The goal is just to enjoy it and force myself to improve as a developer. Oh! Hello, Idalara. No, the Annas are not back. But we do have Shelina, also known as Well Known, and Hazel451. The Annas are probably asleep, yeah. Oh my god, the Annas. So I saw the statistics from that stream after the Annas had been going crazy. I think it was like 500 messages sent during that stream. Oh no. Oh no. I don't think you're one of the Annas. I hope you're not one of the Annas. So, Ida Laura, I am currently working on the back propagation of the neural network. That... Wait, what are your... My sales? What? My sales or... Oh no, oh now I remember. Oh crap. Oh... they were talking about sales, I don't know. But I'm pretty sure that Well Known is also talking about sales right now. It's always about sales. You gotta get the money, you know. I gotta be able to pay rent. So, first thing we need to calculate is how this cost function is affected by the activation function of the output layer. So when we're done that, we'll see how the activation layer is affected by the pre-activation, and then how the pre-activation is affected by the weights and the bias. It's nice to see that you guys are chatting. Okay. We need to find the derivative of the activation function. And the derivative of the activation function I've already calculated actually. So basically take del divided by del A3, which is the prediction, of 1 divided by n times sum. Oh, got something in my eye. Sum goes up to n minus 1 as we're looking at indexes. I equals I equals 0. There we go. Then AI3. Wait. What am I doing here? What is going on there? Yeah, I'm not messing up now. Never mind. Okay. Like that. And this should be equal to 2 divided by n times sum n minus 1. Then we take I equals 0 as we start at 0. Subscript I, subscript 3 since we're looking at the output. And the realize, so this is the derivative of the cost function. Let's delete that crap. Right, check Discord. Let's see what's going on Discord. I will send you a response right away. There we go. Just replied. And we seem to have a new person on the stream. Welcome. I hope you two are having a great evening. And I hope you enjoy math and programming, because that's what this is about, as you can see. So we're gonna implement this in code, the derivative of our cost function. We're gonna scroll up to our math class. We have these static methods, and we're gonna define d damn. You don't wait a minute. Why would it suggest that we remove the mean squared error? This is interesting. So it claims the derivative is simply the prediction minus the true value. This is strange. This is very strange. I'm gonna Google this. Mean squared error derivative. Let's see. This guy says. To get that, I'm gonna zoom in a bit for you. I think that might work. So the derivative of 1 minus p to the power 2 with respect to y, the target is blah blah blah. Yes. But what happens to the summation? I'm gonna look at another link. What is the derivative of the mean squared error? Partial derivative of the mean squared error with respect to weight, Paris burst, blah blah. What is estimation? T. They are using very strange variables here. What is T and what is O? What happened with the 2? Mean square error is this. I want the... Okay. Do we have any secret math geniuses in the stream? Because when I tried to... Wait. The derivative to A. Yeah. No genius here. Fuck. It was worth asking. I mean, you never know. I had a very helpful programmer in the stream the other day who let me know when he found errors in the code I was writing. It's so convenient to have him there. Mean square error derivative. Show me the derivative. Okay, so here, those are the weights, yes. Times the times the what? Outer, inner. Oh crap! Yeah. Okay, I might see where I went wrong here. Outer times inner. Poof, poof. Yeah. Oh my god. Let's bring up the painting website. No, did I close it? I think I closed it. No, it's here. Oof. False alarm. Welcome to the stream, by the way, everyone. We seem to have even more people watching now. Okay, so this math is not really correct. So we are gonna take a step back and remove this. Okay. Gonna grab the pen here. See if we can move. Oh. Okay. Give me a second. Move the dot. Okay. This tool is not great, but it's enough for what we're doing. Okay, so this will not change. So we're gonna have 1 divided by n times sum n minus 1, since we're looking at indices, or to say indexes, I'm not sure. Like that, and take the outer times the inner derivative. So get 2 a I superscript 3. This is to clarify that we're looking at the output from this example neural network on the right. I'm going to subtract y1. This is a prediction. Now we're taking the outer, and we're going to multiply this by the inner derivative, which is simply a I3. That should be correct. I hope. Outer times inner. It sounds right to me. Let's rewrite this down here. So we have 2. Wait, what will happen here? This is interesting. This math. So this depends on where we are with the sum. They have written I up there, the J. It's very interesting. Maybe we're overcomplicating things. J. So wait, how does this work? X, that's input. That is that one. So divide that. That's correct. Okay. So this is this might turn into a matrix or a vector, or even a matrix in some cases. And we're gonna check one more search result on this. Let's see what they have to say here. Also, H0. Horrible naming schemes. How can you solve this? This one means square error. Wait. However, I'm struggling to figure out the solution, especially the last X, J. Yeah, this guy is struggling with the same thing. This math is batshit crazy. Okay. The derivative here is a partial derivative of the equation. Yeah, no shit. Partial derivative means differentiation equation with respect to just one variable. I know. In this case theta j, and keeping the other variables constant. Our ratio is used. Wait, j. Wait, that's. They are writing these functions strange. It's like they aren't really using the math they're writing. It's more like they're just doing the math. Like the indices aren't correct. Oh, haha! Here we go. I can download this picture. Let's go to save this to downloads. Okay. We have our cost function here. We wonder what the derivative of it is. And oh, yeah, not sure what that word is. Maybe it's just, or maybe it's Jesus. I don't know. That's over averaging all the loss functions after summing up the derivative by m. We get the derivative y MSE 2 blah 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 times that one, where that's j. Whoa. My mind just got blown. Huh. I need to sit down better if I'm gonna be able to handle this. Okay. We see. What do we see? X. Wait, X. Power rule first, and the chain rule. Okay. This one. there. We are derivative from C. Wait, minus. Why do you subtract the bias? You should add the bias. Wait, should you? I think so. Am I overcomplicating this? Oh, let's see. When will we apply this? Will we apply this in the beginning? And this is just for a single one. I'm gonna see what Colab has to say about this. Okay. Oh, okay, that's a lot of text. I'm gonna open it up on the side here. The private code defines a function called the MSA that detects to blah blah blah. In the context of machine learning, the mean square is going to use the loss function squared. It didn't give me a lot to go on. Let's take a break from that and go to the model. We're going to create a training function called fit. Def fit is going to take 2 arguments. It's going to take well, first self, then dataset x, and what x and y. And then we will let's call it fitting function. Use for training. Okay, but that's not enough. We're also gonna have to take a learning rate as an argument. We're gonna have to take epochs, and what else? We're gonna take, maybe we should start there. Did I ever decide for which optimization algorithm? Let's for epoch in range epochs. Yeah, so it suggests here that we for each epoch, which is like a run, look through all the data. We select the input and output. We make a prediction. And then we call the backward propagation function in this in the model. I'm gonna have to send it the prediction, the output, and the learning rate. Yeah, the learning rate is obvious, so we're gonna have to send. is it? Yeah. Backward. Yeah. This is logical. So no real math will be done here. We basically just manage the amount of epochs and send it forward. So the fitting function is to call the back propagation function a certain amount of times. So if we create backward propagation function, it's going to be called backward. It's going to take in 3 arguments. First we have to type self, then ypred, ytrue, wait a minute, output, that's ytrue. Y predicted, ytrue, and learning rate. Let's see, when we do that, we're not gonna look at that. I think we'll have to start by calculating derivative to see the A. And this is cost function. We're not gonna call it the cost function. Ooh, we need to access the derivative of the cost function. Here we have selected cost function. Then in the cost function, we need to somehow grab this. Can we do that? Is that possible? Yes, it is in multiple different ways. Let's pass it as an argument for now, I guess. That should be fine. Okay. Or. I have an idea. So we're gonna create a setter function. And it's gonna have switch. Wait, is it case? How do you make switches in Python? Let's see what Copilot has to say. Wait, Python doesn't have switches? Python switch. Switch statement, switch case, example. There's no switch. Wait, match. We have match. I think match might work here, so we can use match. Match cost function, and then we're gonna catch MSE. Let's turn this to lowercase. Okay, so just type lower, perfect. MSC. Const function not supported. Yes, that's a great value error. And then const function MSC. Yeah, this is great. This will be perfect. Okay, so now we're gonna instead of doing it like this, we're gonna type set cost function MSC. Let's run all. Beautiful. Not a single error. I am impressed. Very, very good. Very good. Okay, so I'm sorry if you can hear my neighbors screaming. They are going nuts about, I think, some football finale or something. Don't know, don't care. So I'm gonna go to the backward cost derivative cost function, and this is the problem. We need to understand the derivative of it. What to have? I'm gonna go to the math class here. It claims that this is the derivative of it, but I am not convinced. I want to find a good explanation. The ones I was looking at. Here we have something. This looks promising. Oh shit, the website does not look promising. This is not beautiful. Oh. Okay. It hurts my eyes. Compute mean square error slash loss between targets and predictions. Okay, so do the zooming for you. Prediction minus target and square that. Then we divide by the amount and we sum this up. Yeah, this is correct. And here suddenly, wait, this derivative, yeah, that's a gradient. Wait, is it the gradient we're looking for? Not the... Just gotta reply to the message here. So gradient here. So once again we divide by all the amount of, what do you say, predictions. Compute mean squared error gradient between two targets and predictions. Wait, between targets and predictions input prediction and k array, turns and k arrays. The averaging is only done over the output node, not over the samples in the batch. Therefore, we get an answer similar to PyTorch. One must divide the result by the batch size. Batch size is the amount of predictions, basically. But why? Why? I want to see my math again. We keep this, that. This one never shows up, and this one is removed. Wait, am I forgetting something? Isn't derivative gradient the same thing? Directional derivative represents a rate of change of a term. The gradient can be used in formula to calculate the directional derivative. The gradient indicates direction. Okay. Do I need a video on this? What is the difference between the gradient and the directional derivative? Oh. Gradient is a vector. The directional derivative is a number. Is the rate of change that you're pointing to. But we are looking at the derivative, not gradient. Why did they take the gradient? Loss. We have. Wait, what did they do here? Number implementation. Okay. Loss derivative. So many ads on this website. QPL implementation. Open source array library. Nah. We're not gonna try to improve the math speed now. This. Maybe. Medium tends to be great. Okay. Scroll down. One dimension. Learning rate. MSC. Blah 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 blah. Okay. Yes. The weights. That's the same thing as that. I got so far and sent this. Wait. Yeah, I understand it. Oh, that's why the other guy's method was so weird, because they just like this guy didn't include the bias in the math. Don't remove like the common parts from the equation. Don't simplify that way. Okay, so you get exactly. This is what I found. When taking the gradient of the MSC with only one weight, the derivative can calculate with respect to... Okay. We got so far 2 weights. What the fuck? Why do we suddenly have XI out there? Huh. Then we'll get 2. That's not right. A3 times A3. Maybe A3 is a constant. So we could just implement that. We just implement this because it's all one weight. No, wait. Wait. Damn, my head is spinning from this math. Okay, we look at the cost function. The derivative of the cost function. Cost function looks like this. AI subscript 3 is A. That's just constants. So I don't see the problem. It's an activation function. So I think this is this is correct. 3 weights get simplified to this. Yeah, I think I got it. This is I think this is correct. So we're gonna stick with that. So let's convert this into code. Okay, we have I sure hope this is right now. 2 times NP mean. In there we're gonna take y dot pred. Wait, will this work? It's gonna be constant, so it's gonna be multiplied by that value. Welcome to the stream, by the way. I'm trying to find the derivative of the mean squared error function. And I'm thinking if this is correct, if this is gonna work. Will it? So this. By the way, I hope you're having a wonderful evening. I know I am. Sitting by the computer, writing code, doing math, living the dream. So, do you have any suggestions? What should I try? How should I try this? I personally think if we give it to... will that work? Okay, I'm going to try some matrix multiplication here now. So we got a NumPy array. It's a let's say we have 1, 2, 3, 4. Perfect. No, let's 1, 2, 3. That's it. And I'm gonna multiply this by that. Damn, it works. So this should be correct then. If you haven't followed, by the way, make sure to follow if you enjoy watching people write code, math, and struggle with it. Might also do some gaming every now and then, just because it's fun. Okay, that one's done. Perfect. So we have the CTA, and now we're gonna pass this to that layer. Wait, should we? We need to. Let's type DZ is equal to DA. Whoa. Huh, like that. Damn. Anything else would be crazy. Okay, we're gonna look at my math here to the right and see how I calculate DZ. But we know that DZ is the step function. So the step function is located up here in our math class. Here, that's the derivative of ReLU, and we want to be able to access the derivative of this one. Well, we won't be able to access this in a neat way, because the way we select ReLU is that we do it when we create our model here. So we're gonna have to write this like so. So we're gonna pass strings instead, and you'll soon understand why. Okay, so we take a layer, we pass the activation function to the layer to a dense layer. We have our activation function, This is gonna be none and self dot under dot derivative underscore activation function is gonna be none. We're gonna format this a bit, make it a bit more beautiful. Okay. And we're also gonna set activation function. We're going to find one more function here for the dense layers. So it's going to be private and set activation function. We're going to use a we're going to make it lowercase. Activation function dot lower, and then we're going to use a match. Match for the lowercase version of the activation function name, and if it is relu, then we're going to set the activation function to relu and the derivative of it to the derivative relu. Otherwise, as a default, as a fallback, we're going to return an error. We're going to raise an error and say that activation function is not supported, which makes sense since it's not located here. Okay, so we're gonna just copy the name here. We're gonna send the arguments there. Right, we have to type self. Let's add a comment, set activation function. Yes. Okay. So that means we should be able to access the derivative now of the activation function, but yeah, it's safe. Never mind. Activation function. Let's make this long. I know that my properties have super long names now, but bear with me. It's good for the readability, at least for me now, because this type of work makes me very confused. Okay, where will we go now? Oops. We're gonna go to the to the backward function in the model. Yes, the private one. Here we go. So we will look at self.out. Wait, no. We're gonna look at self. Derivative cost function. No, that's wrong. Self dot tail layer. Yeah, tail layer derivative activation function y pred. That is correct actually. That works well, but is it clear enough? I don't think so. So we're actually gonna write. We're gonna have to store the outputs from each layer. So we're gonna go to a layer. After the prediction, forward output. Return. So we're gonna set self.output. Oops. Output equals sure. Should we make a numpy array or should we just store it right away? Let's make a numpy array out of it. Output. Okay, so for the forwarding, create a list to store the output of each neuron. Perfect. Store the output for back propagation. and then pass output to the next layer, if any. Yeah, very good, very good. Next we will. So we're gonna type self.tail layer.output like that. It's a bit clearer, because if you just read this quickly, you don't understand that the y pred is the same as the output of tail layer. Tail layer, by the way, is the last layer, which is also the output layer. That's important to keep in mind. Let's run everything, just make sure it works. No crashes, no errors. We do have an error here. Yeah. We're gonna have to change back activation function underscore name to just activation function. And run. Oh, not restart, run. Okay, and we're back on track. I do not like the claims it's an error there. Okay, fixed. Okay, so we have calculated these two. We're gonna pass them along now to the previous layer. So let's type no. It's trying to. I don't want that. No. Okay, so self. Or do we? Let's see what it suggests. Okay, so it suggests we look at the weights now. We take the off blah blah. Why would it even suggest this? Like, the thing it suggests right now is that we just basically ignore all the other layers but the output layer. I don't know. This is, it's just wrong. Okay, so self.tail layer backward. We're gonna pass it the derivative. The derivatives multiplied and the learning rates. Perfect. Okay. Now that we've done that, we can reuse that. So we're gonna scroll up to a dense layer. Backward pass. This is the learning stage. Okay, so it cannot be private, so we're gonna backward self error. What the hell? I mean, sure, we can call what we are calculating the error, I guess. It might be confusing. I don't know. Learning rate. So we're going to start by calculating the error that is correct. So we're going to have the said the dv a. That's b is just going to be the same. Think so, at least. How is defined? Blah. Yes. Yes. However, the Z, the V is not the same. So I'm not gonna have my cursor there, so because I don't want the AI to just suggest a solution for me. Instead, I'm gonna look at the math I've done on the right here and see what it should be, and it should be times that layer's input. Interesting. So self dot previous layer dot output, because the output of the previous layer is the input of this layer. I'm just gonna make sure that the output is also fixed by the modified by the activation function. It should be here. Yes, it is. Beautiful. So now we have these two. Now we're gonna up. Right. Because we add the neurons. Interesting. Set the A. Why do you want to set that equal to the weights? So when we update, we will subtract that times the learning rate. So let's add a function in the neurons as well. Adjust weights and bias. Yeah, define adjust. Well, this is not backward. It's not really backward propagation. Weights gradient, bias gradient, and learning rate. So now it's gonna be able to suggest this for us actually. So as we see, we take the weights, we subtract the learning rate times the weights gradient, and we do the same thing for bias. This method is called during the backward propagation propagation step. Perfect. So I guess for neuron in self.neurons we're applying dot products here. This is one of the things with autocomplete code that is dangerous. Some people just go along with this, but you gotta make sure that you understand what's going on. Don't just follow it blindly. Okay, so it wants us to do So we gotta keep in mind here that we might have been given an array. The error might be an array, I think. Wait, why error? Isn't it gradient? There we go. And the weights are going to do dot product there. But we can't take all the weights. So we can instead use I in range of the length of the neurons. There we go. Let's see. So suggest we multiply the gradient. Self-derivative activation function. Okay, let's go back. We're not gonna do it like this. So, self dot neurons I. We're gonna adjust. That is correct, and we're gonna send it first for the weights. Alright, this has to be multiplied by gradient. Now pass these alongside the learning rate. We also have 2 I. I'm not sure if this will work because wait, gradient times gradient. That's just gradient, sorry. Let's move this one to the other side to make it a bit more even. Beautiful. And also gonna have to, if any, so if there is a previous layer and it's not input layer, if not instance is instance self previous layer, if it's not an input layer, then we're gonna pass some stuff there. But the input layer is defined down there. We could move this layer beneath the input layer. Let's copy this. Delete it. Beneath the input layer. Paste that in. And we're gonna type pass here for now. Okay. So send the create its bias and gradients there. We might have to convert to NumPy arrays and send the gradients to the neurons. Perfect. And now that is done, we're gonna compute the gradient for the next layer. Let's see. Gradient. So for the next layer, I'm gonna have to calculate the Z, the A again, and the Z, the A is good question. Good question. That's good soda. Why is not soda? Sorry, I lied. It's Fun Light. It's not as good, but it's cheap and it's better for the teeth. The A, the Z is always going to be a stepper function. But it claims it's something else. It's the gradient times. That looks weird. How is A affected by... Wait. Set the A. Yeah. Self dot previous layer dot derivative activation function of that one's output, I guess. Wait. Z3A2. I'm making a mistake here. I am so sorry. It is indeed it is indeed a dot product, I think. I'm gonna look at the math here. Set A. Yeah. It's definitely dot product. MP. Dot. Gradient. Dot product with the weight. Neuron weights from. Yeah, that is true. We're gonna select the weights from each neuron. Get that transposed. Wow. This is getting weird now. Let's see what. Just gonna check message here. Okay. So we have calculated that. I'm thinking, should the back propagation go via each neuron instead of the layer? Is that better? So we're to send that to each neuron. That neuron needs then to know which neurons it's connected to. Huh. Interesting. But then maybe I would go away from this concept. I think let's try this. We're gonna call this a array. Because we're gonna transpose this. I think. Do we need to? I feel like the math, the back propagation should go via the neurons in a way, because they are the ones adjusting. The layers are basically just holders. Where do we read the outputs? If we go to model, you look at the output. Set the A. Let's maybe try this in a way. I have to set the A. Also need the A to Z. The A to Z is self.previous layers due to activation function of the outputs. Is it though? I think think I see an error here. The output is what comes from the activation function. This is not the alt calculator, it's sed. So let's call this sed. We're gonna have to grab the sed values. Weights is the output, so that one can call A. This one is sed. Here, let's define self.output. No, self.a. None, self.sed. None. Perfect. So let's look at these. A. Pen part A. Blah 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 blah. We're also gonna have sed. Yes. It's gonna be empty. We're gonna store that one too. And like that. Perfect. Part Y. Wait, why do I type sed? Oh my god. Yes, that's the activation function. Or Y. Depends on how you see it. Let's go with sed then. And we can then scroll down to the... Oh, here we have it. Times sed. Yes. And I guess self.previous layer backward, we'll multiply those two with that, and that will just go on. So if now run everything, let's look for errors. None, that's good. Dense layer is not defined. I know that dense layer is defined for a fact. That one's just stupid. So set the cost function, we look at the shape, do the test there. And let's see. So run through. Take one at a time now. Certain. Wait, amount of times, all of them for each. Wait. Okay, so upon fitting, set number of epochs. We have an input and output. We predict, and then we do that. I think we're gonna implement batch size. And this is gonna have to be changed to length x, batch size. Is that correct? I think so. So you're gonna take those steps. And I'm gonna have to delete that data. And on the backward propagation, we do that. Let's try. Alright, after each epoch, we are gonna print class function let's type, you know what, let's just go crazy here. Oh, that looks good. I think that will work. Oh, this is where we use validation set. But let's not do that. There's an X epochs. I think this will not work. Like I said, it will not work. I knew. Okay, so it has something to do with this, I think. I'm gonna have to look at this. What does this do? Okay, the length will be 1030, batch size will be 32. Let's for I in range. No. In range, print I. It's not. Start stop step. Right. So basically start at I. Stop that thing. Wait. There we go. So I had to add the I here somewhere. Oh, it's already added. Hey. Okay, let's run everything again. Yes! Crash! Woo! Local variable I referred before assignment? Ew. I guess just 0. Okay. Now we're talking errors. Damn, it went so well without any errors for so long. Okay. Orbit self head forward, blah blah blah. Wait, we have. I see. I don't. Wait, it's during the forward pass for some reason. So if we perform a prediction of all of these, it works, but not here. That is odd. This X. I think we mess up something with data here. Probably. Let's print out I. Like that, I guess. 0 to 31. If we have an array here. And try to select 0, 1. Okay, that one. Wait, what? So it stops at that one. That's good. So that should give us. Stops at 32. So good. Should get 32 then. Okay. What if we only do it one by one? You know? Do all. Just one at a time. And let's check how. For I in range 5 print I. So it excludes the highest number. Okay. Then we'll pass the i's here. Okay. That's something. Okay. Unsupported operation for types. Multiplication float and generator. So this is probably the generator. This set the A. We're gonna go to that line. And I want to see. Let's just do it like that. We run it, and here we go. We get the weight. Is this during the first propagation? We need to know where we are in the algorithm, so we're gonna print this out. Let's print out. No, let's just do print, and we're gonna self.name. It's good enough for now. So we are actually on the output layer. Okay, perfect. Well, I think it's getting late, so I'm gonna have to end this stream now. But thank you so much for watching this stream, and have a great evening.